Hello everyone and welcome back. So this time we're going to go through an example calculating the moment. I'll be using the scalar formulation this time. So it's fairly simple, but not necessarily easy. And let me get my pin out. Here we go. So first off, actually I'm going to use the scalar formulation. I don't want to use the scalar formulation. This looks terrible. Oh, now we'll use the scalar formulation. We'll use the scalar formulation. We'll see how it works. Sorry, I can change my mind. I'm your teacher. So, given a 100 Newton force, it's applied to the frame like so. You see it right there. And we need to find the moment of the force at point O. So we're going to have to create some sort of position vector from here over to here. Okay, so with that, it shouldn't be too terribly difficult. I mean, all the numbers are given to us, but let's work it out. So, what we're going to do, we're going to resolve the 100 Newton force along the x and y axes, and then we're going to determine I'm not using a scalar analysis. Scalar analysis works great in the end. It's actually the same exact thing as using the vector formulation. So only for 2D though. 2D. For 3D it's very different. But we can do this. So I want you to pause, try it out, and then come back and we'll look at it together. So 3, 2, 1. Okay, hopefully you've paused, you've gone and tried it out. And now let's look at the example together. So first off, we have to get this into components. Now, luckily for us, it gives us a slope triangle, which means we don't have to worry about any sort of trigonometry because it's already there. That component right there would be 4/5 of 100. So the x component is 4/5 of 100, which is 80. And the y component would be 3/5 of 100, which is 60. And 60 right here. Now, the second thing we need to do is to figure out the components of our position vector, which are honestly just given right here. So that makes it pretty simple. And then we take the force in the y direction and multiply it by the position vector in the x. And the force in the x direction, and multiply it by the position vector in the y. Okay? Force y, position x, force x, position y. And is this a minus sign or a plus sign? Well, as you see right here, that should be a minus sign. If you're really uncertain, don't worry about it too much. I usually tell you clockwise is positive, counterclockwise is positive, and then you can just figure it out from yourself. If you can't remember which way is going to be clockwise, which way is going to be counterclockwise, draw both. So if this is the force in the x, and this is the position vector right here, then, oh, look at that. It curves like that. Be very careful how you're doing the cross product. And let me actually erase my screen because I'm getting way too much stuff right here. And there we go. And back to our pointer. So if we add all of that up together, we get negative 460 Newton meters, and that's counterclockwise, not counterclockwise. Good my goodness. Negative 460 Newton meters counterclockwise. Sorry, clockwise. And we have it. So, with that, with this, we're done. That's all the scalar formulation requires. We break things into components, and we make sure that we do the opposite components. Y times x, x times y. And you'll do well. You'll get the problem right. So really, really, really dig into this. You are effectively taking the determinant of this matrix, so if you forget anything else, you can look that up if you want to. But this is a very simple formulation, so please try to memorize it. Well, I hope this helped you, and next time I'll go over a few more examples about how to calculate the moment using the cross product. See y'all then. Bye-bye.